In our last physics class, we spoke about electricity direct currents, so where we talk about the the charge body, the motion, current, and all that. So let's recollect that we spoke about the force EMF E. So and we also talk about the current I, resistance R, and internal resistance R of the cell. So and the formula that combines this is I equals E over R plus R. So where these have to be the the product of I and R is the external resistance, external voltage, while I and R is the lost voltage. So if you can recollect this, so and then I said it that you have to connect the external resistance parallel to uh, the voltmeter. So we are going to talk about how the parallel connection seems to look like in this video. So but let's quickly look at today we look at electric field first. Electric field. So when we say electric field, what does it mean? Okay, let's take for instance in the earth crust. Within the earth crust, so if the earth is represented with a circle, the center of the earth, there exists a gravitational force that attracts everybody towards the center. So this is the gravitational force. We can't see it, but it always acts. So which means there is a field around anybody in the earth crust, and that field is gravitational field. So similarly, when a charged body exists, there is a field around them, so that is electric field. So we can define electric field as a space or region where a charged body experiences the effect of electrical force. Now let's look at a positive point charge, a charged body with positive charge. So you see that they act in the outward manner. So then for a negative charge acts in a inward manner. So this line you're seeing is called the line of force. So the lines cannot be seen, but they are just imaginary lines to represent the direction of the field. So that is it. So we saw the field this way. So this kind of line of force is called the radial line, because if we draw a circle around it, it seems to be like the radius of the circle from a point charge. Okay, so that is what we call field. So we will be looking at also some certain things we have spoken about before. We just have to expatiate more on them, just like so that is it. We're going to talk about what potential difference is, though we've discussed it in our previous class, but we just have to expatiate more on this. So after talking about the radial field, so that is just what electric field is. So now when we talk about the power supply and potential difference, so potential difference, potential difference. So potential difference is just like the work done in moving a charged body from one point to another in a circuit or in a field. So, and you can also define it as the the energy that is supplied per unit charge. So the potential difference is denoted by V and also measured in volts. So potential difference is equals to the energy supplied per unit charge. So you can define it as the energy supplied per unit charge in an electric field or in a circuit, and you can also define it as the so that is it. So these represent the energy donated, supplied per unit charge in an electric field. And according to the Ohm's law we discussed in the other class, we have V equals IR. So these are the formulas to calculate potential difference. So potential difference is just something that is key because we can use it to explain why a bulb brighten up. So when you see a bulb, take for instance you have a bulb, an electrical bulb glowing. So this bulb gets lighter when the potential difference goes higher. So which means the higher the potential difference, which you can call voltage. So voltage is just a potential difference between two specific points. So when we say the voltage is high, it means the potential difference is high. And then that implies that the bulb will light more because the bulb receives more energy when the potential difference is high. So, and the bulb is meant to convert this energy into light. So, which means the more energy it receives, the more brighter it would be. So, that is that on the potential difference and the energy. You get that? So there are relations based on that. So the number of batteries, and there is a way you connect batteries to give you more potential difference, and you talk about the connection of batteries and series and parallel. So but let's uh, leave that. So we understand what potential difference is as related to energy and current with resistance. This is Ohm's law, and this is the another basic definition for potential difference, and this is the implication of potential difference on bulb. You get. So now we are going to move to what we call okay, the measurement of current. So when we talk about measurement of current, a device is used to measure current, and that is ammeter. So take for instance, we have a cell. This is a cell. Are you getting it? So the cell supplies current. This, the longest side is the positive terminal, while this is the negative. So you connect a cell to an ammeter. Ammeter is the device that is used to record current. Okay, alongside, let me just make this circuit a complex one. I mean, not really complex, but I want it to contain the resistor R, and also, so that's resistance. I want it to be connected to potential difference, I mean voltmeter rather, in parallel. So I will explain this parallel arrangement and what I mean. So when current is supplied from the positive terminal of the battery, so the current gets here, which this place is called a node or electrical junction. So this point, you call it a node, and this is also a node. So these are the only two nodes that we have in this circuit. So you see all these, they are not nodes because current is not splitting at those points. So current just pass straight, and here it got splitted, and the potential difference is recorded here. So the potential difference that is recorded here is the same as the potential difference across the resistor. And then the ammeter here, we measure the magnitude of current I. This will measure the magnitude of potential difference of voltage V. So those are the two devices. So now we have talked about current in our previous class, and this is how to measure it. We have talked about potential difference in our previous class and now, and this is how to measure it using a voltmeter. So, and then this resistor, we need to talk more about it. So don't forget this cell as EMF E. Are you getting it now? So, and then all these are related with, just like I've said, I equals E over R plus R. So meanwhile, this internal resistance R will be within the cell, that is R. Okay, so now let's dive into what is called the resistance, and then this form of arrangement of resistance we may have. So when we say resistance, resistance is just like the amount of opposition given to the flow of current. Like I've said before, that when a charged body moves in a circuit or in a conductor, there exists a kind of frictional force, so which is resistance. Okay, so this frictional force enables them to move in the circuit, so we call that resistance, denoted by R. Now, what is the difference between a resistance and a resistor? A resistor is a device that offers resistance. Don't forget, uh, all electrical conductors have resistance. And at the same time, you can create a device that will offer more resistance. So those are external resistors. Okay, so now when we have a circuit, this is a circuit where you have the cell connected to, okay, a single, okay, let's take it this way. This is a resistor here. So, and then you have the current flow. So if the current flows and pass through this resistor, so the resistor is connected in series with uh, the source of the current, which is the EMF. So this is resistor connected in series with it. So what does it mean by series? The amount of current that leaves the battery is the same amount of current that gets to the resistor. So that makes them to be in series. So now you can connect resistors, more than one resistors in a circuit. You can connect more than one resistor, and there is a specific arrangement. Take for instance, the values of resistance are measured in ohms, so you can have values ranging from 1 ohm, 2 ohms, and so on. So now if in a circuit I needed 1 ohm but is not available in my laboratory, so and I only have 2 ohms, so all I have to do is to connect the 2 ohms, like maybe two of them, in certain arrangements so that they will give me 1 ohm. And probably in the other way around, I might need 2 ohms and all I have in my lab is just, let's say, 1 ohm. So all I need to do is to connect my 1 ohm in just like maybe two of it in a certain arrangement to give me 2 ohms. So what are the two possible arrangements we can have for resistors? We can have resistors being connected series, and we can have them be connected in parallel. So what is the implication of connecting resistors in series, and what is the implication of connecting them in parallel? So we're going to discuss that now. So if we connect resistors in series, so let's draw a diagram to show that. So let's look at these resistors connected in series. I love using this symbol for resistors. So this is resistor R1, this is R2, this is R3, and this is the source of the current E. So when the current flows, you notice that the current that flows from the battery is I. It is the same current that we enter here, I, you get, so which means I, so they have the same current flowing through them. But because the value of the resistors are different, so they will have different potential difference. Don't forget, potential difference is the product of I with R. So which means so far the resistance are different, despite they have the same current flowing through them, the potential difference will be different, because here you'll be having the first potential difference would be V1, V2, V3. So that's a very different potential difference. So because if I have V1 is going to be I multiplied by R1. So the V2 is going to be IR2. So then the V3 is going to be what? I R3. So for the fact that the resistance are different, so the potential difference will be different. So which means the total potential difference in that circuit, that is what happens when you connect three resistors in series. Okay, so or more, if you connect three or more in series, so these are what is taking place in the circuit. Okay, so then you would notice that the total voltage is going to be what? V1 plus V2 plus V3. So don't forget, V equals IR from Ohm's law. So this will be the value of the total resistance. So if the value of the total resistance is this, so then we can also have I, R1, just like I've analyzed here, plus I, R2, plus I, R3. So by the time I factorize all the high, I'm going to have high multiplied by the total resistance equals high into R1 plus R2 plus R3. This is just to derive a formula for resistors and series. Okay, so then the I will cancel I, so which means when you connected 3 or more resistors in series, the total resistance in that circuit is, when you sum all the resistance together, R2 plus R3. So then we put plus dot 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 Rn. That is if you connect more than 3. Okay, so that is it. So whenever you have a 1 ohm resistor and you need 2 ohm and the 2 ohm is not available, you can just connect 1 ohm, 2 of 1 ohms in series, and you would get 2 ohms. So that is what this formula implies. Okay, so then we move to the parallel arrangement. So when resistors are in parallel, okay, when resistors are in parallel, so look at this, you have the parallel arrangement of resistors. So let me give an instance of that. So this is the cell. So let's assume you have the resistors, one connected here, one connected here, and the other connected here. So this is R1, R2, R3. So now the current produced in this circuit is high. So when it gets to this place, this is actually a node. This is also a node because the current will split. Okay, so then are you getting it now? So the current that would enter here, the current will be splitted in such a way that the value of the current here will be I1, I2, I3. Take note, the current is not splitted into 2 equal parts. It is splitted in such a way that the potential difference of the 3 resistors will be the same. So they will have common potential difference, but different current. So in that wise, the total current in the circuit, I total, which is this, is going to be equals to, don't forget, I1 plus I2 plus I3. So don't forget, from Ohm's law we said that V equals to IR, so which means making I the subject of formula, we have I equals V over R. So we can transform all these, so we can have the total potential difference over the total resistance for this. Are you getting it? All equals the potential difference over R1 plus potential difference over R2 plus potential difference over R3. So this is like this because the potential difference in the circuit is the same as the potential difference across each resistors because they are connected in parallel. Okay, so by the time you factorize this, I think you have V1 over R, so that's a total resistance in the circuit, equals V into 1 over R1 plus 1 over R2 plus 1 over R3. So then this goes with this. So at the end of the day, if you want to find the total resistance in the circuit, you just have to add the reciprocals of the connected resistance, 1 over R3 plus dot 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 1 over Rn, that is if it connected more than 3. Okay, so that is the case. So by the time you want to solve for this, you just make RT the sort of formula. That's the total resistance in the circuit. So which means if you are connecting, if you needed the 1 ohm resistor and you have just the 2 ohms, if you connect them in parallel, let's take for instance 2 ohm resistors connected in parallel. So which means the total resistance is going to be 1 over 2 plus 1 over 2. Okay, so that will be 1 over R equals 1 over 1. So by the time you turn it upside down, the total resistance in the circuit will still be 1 ohm. So that is it in case it might be applied. Okay, so then we can have a mixed circuit where you have the series and parallel, so you just have to get that yourself. So we are going to solve questions on that when we meet in class. So when you want to analyze a circuit to know the ones connected in series and parallel, you just have to identify the nodes. So the nodes which I told you, the electrical junction where current split, Don't take this as a node is not a node because current is not splitting here. So current only split when they got here and here. Okay, so these are the nodes. Do you get that? These are the nodes. So and then there is a special case when you have the special case is if the resistance connected here are the same value. So that would be magic, they will drag the same amount of current and we expect them to have the same potential difference. So that is a special case in terms of connection of resistance. So when we meet in class, we talk about the arrangements, the mixed arrangements where we have to analyze and find the total resistance in a circuit. You might be given a complex circuit where you have more than 10 resistors and then they are arranged in such a way that you have to select the series, select the parallel. After doing that, then you find the total resistance in that circuit. So we'll meet and solve those questions in class, okay?